The simple question: why does light from distant galaxies look redder? And it leads us to one of the greatest discoveries of all time, the age of the universe itself. Imagine trying to measure the size of something not across a room, not across a country, but across the entire universe. We can't stretch a tape measure to the edge of the cosmos. Instead, astronomers have learned to use light, the oldest messenger, and the physics of cosmic expansion as their rulers. This story starts with a simple question: why does light from distant galaxies look redder? And it leads us to one of the greatest discoveries of all time, the age of the universe itself. When a galaxy moves away from us, the wavelengths of its light are stretched, making the light appear redder. This phenomenon is called redshift, denoted by Z, and it's similar to the Doppler effect you hear when a siren passes by. For relatively nearby galaxies, redshift is approximately proportional to their velocity. V is nearly equal to c into z, where c is the speed of light. Edwin Hubble discovered something remarkable. The faster a galaxy is receding, the farther away it is. This relationship is now known as Hubble's law. V is equal to h naught d, where h naught is the Hubble constant, the present rate of expansion, and d is the distance to the galaxy. But to use this law properly, we first need a way to measure distance to galaxies, and that's where the next idea comes in. So how do we measure the distance to an object millions of light years away? Astronomers built a cosmic distance ladder using objects called standard candles, celestial bodies whose true brightness we know. By comparing how bright they should be to how bright they appear, we can infer their distance using the inverse square law of light. A critical rung on this ladder is made of Cepheid variable stars, stars whose brightness pulses regularly. Henrietta Leavitt discovered that the period of a Cepheid pulsation directly tells us its true luminosity. Longer periods mean brighter Cepheids. Thus, by measuring a Cepheid's pulsation period and apparent brightness, we can calculate its distance using this formula, where small m is apparent magnitude and capital M is the absolute magnitude. Using Cepheids, Hubble was able to measure distance to nearby galaxies and proved for the first time that Milky Way is not the entire universe. However, not all galaxies' motions are purely from cosmic expansion. Galaxies also have peculiar velocities, random motions due to local gravitational interaction. For example, the Milky Way and the Andromeda Galaxy are moving toward each other despite the overall expansion of space. In Hubble's original data, these peculiar velocities showed up as scatter around the perfect straight line expected from v equal to h naught d. But for very distant galaxies, their peculiar motions are tiny compared to the grand cosmic expansion, a pattern called the Hubble's flow. Underpinning all this is a fundamental assumption, the cosmological principle. It states that the universe on large scale is homogeneous and isotropic, which means it has the same average properties everywhere and it looks the same in every direction, respectively. This principle allows us to treat galaxies at any location equally and to apply the same laws of physics universally. But in an expanding universe, even the idea of distance needs precision. There are two key types here: proper distance and comoving distance. Proper distance is the actual physical separation between 2 points at a given cosmic time. It grows as the universe expands. Comoving distance is a distance measure that stretches along with the universal expansion, keeping coordinates frozen. Imagine dots on a balloon. As the balloon inflates, the dots move apart. The proper distance between dots grows. The comoving distance stays the same on the balloon's original surface. In mathematical terms, it can be represented by this formula, where A is the scale factor, a dimensionless number that tracks the expansion over time. But expansion doesn't just stretch distances, it also stretches light itself. As light travels across the universe, the very space through which it moves is expanding, stretching the light's wavelength. This is called cosmological redshift. The relation for this can be given by this formula, where A0 is the present scale factor, often set to 1, and A of t is the scale factor when the light was emitted. Thus, a higher redshift c means the light comes from a time when the universe was much smaller. More importantly, cosmological redshift is not a Doppler shift from galaxies moving through space. Instead, space itself has expanded while the light was en route. Now let's come back to Hubble's constant h0. h0 measures the present rate of expansion, typically in the units of kilometers per second per megaparsec. For example, if h0 is 70 kilometers per second per megaparsec, then a galaxy 1 megaparsec away is receding at 70 kilometers per second. Interestingly, the Hubble's constant has dimensions of inverse time. Its reciprocal 1 upon h0 gives a characteristic time scale called the Hubble time, an estimate of how long the universe has been expanding. Using h0 approx 70 km per second per megaparsec, we find 1 upon h0 to be approximately 14.4 billion years. This rough calculation already suggests the universe age is about 14 billion years old. We can make this even more precise with just this simple math. In a universe with constant expansion, the age would simply be the Hubble time. However, we know that gravity slowed the expansion in the past, making the universe younger than 1 upon h0. Dark energy later accelerated expansion, making it older. Accounting for these effects, observations, especially of supernova and the cosmic microwave background, show the true age of the universe is about 13.8 billion years. Still, the simple estimate from 1 upon h0 is surprisingly close. By observing redshifts, applying Hubble's law, and carefully measuring cosmic distances with standard candles, astronomers have turned light itself into a cosmic ruler. In doing so, they revealed that the universe has been expanding for nearly 14 billion years, and that every time we gaze at distant galaxy, we are looking deep into the past. It's a profound idea. Light, distance, and time are deeply connected. In measuring the cosmos, we are also measuring our own history and peering into the grand story of existence itself. If you enjoyed this journey across space and time, follow astrophysics for more. There is so much more to uncover.